Welcome back to chemistry. We are finally starting some real chemistry. It's only, 4 weeks into school. We are going to start looking at the structure of an atom. And in order to do that, we're actually going to start a little bit with the history of how we got to what the atom looks like today, because it's all kind of important pieces of the puzzle going back. So as we go through this unit, we're going to first start with a little bit of history, then we're going to look at protons, neutrons, and electrons. After we look at those protons, neutrons, and electrons, we're going to learn about something called an isotope, couple labs in this unit as well. And then finally, we're going to end with the average atomic mass, a little bit of math. Sorry, I kind of blanked on that one. So as we go through this unit, we're going to look at the history of the atom first. In order to do that, I always start off with a demonstration. I'm dropping this video in. It's not quite there yet. I have one thing to finish up with the recording, and then it'll be here. For my face-to-face kids, we're actually going to do this in real time on Monday, but this will have something in there when you actually go through and download your notes. So when you download your notes, I would put it onto your device so that way you can refer back to them as we go throughout the units. There's videos that are embedded that is not me. It's actually like YouTube videos and things like that. There's a few websites to go to. So make sure that you're doing all that. It really helps to get your understanding a little bit better. And then also you have the note paper I dropped into Schoology as well. If you have the ability to print, I highly, highly, highly suggest writing your notes. I know everything seems to be digital this year, but your brain does better when you can actually write down what you are learning. So even if it's on a spare piece of lined paper, write your notes. You can write the question and the answer. You can do vocabulary, something where you're actually picking up a pen and a paper and writing things down. Your brain is going to retain more information, and chemistry keeps building off of each other. So you're going to need to know this information going through the year, even into second semester. Now, this first part is not on the test. You don't need to know this. It's not actually part of the official curriculum. However, people always ask me every year, well, what's alchemy? How does that relate to chemistry, whatever? So alchemy is looking at different elements. They were the original OGs, chemists, whatever you want to call. So they knew about some of the elements. They also thought that things like fire was an element, air was an element. They thought that magnets, kind of behind my picture here, that was an element. They didn't know that it was actually made up of different things. So looking at all of these, they thought all gases were all air. So looking at these things, they actually used them in a few different ways. Again, I'm generalizing this a lot. You can actually take an entire semester course in some schools in just alchemy because it's a little bit of history, it's a little bit of science in looking at different components. But again, generally, regionally, there were three main concepts that people were doing. The first one is in Asian type countries all across that whole continent. They were doing different things with fireworks. Again, generalized. They were taking gunpowder, they were adding things to it, seeing what happens. They didn't live very long because typically they blew themselves off or they caught things on fire. But making fireworks was a big thing that alchemy did for chemistry. Second thing, making the philosopher's stone. Some people thought that it was a substance that you drank. Some people thought it was a physical thing. But either way, they either thought that it had magical healing powers or they thought that it would help you to live forever. Either way, they never found it, but they were ingesting things that they probably shouldn't have been ingesting, and a lot of them ended up dying of mercury poisoning, Mad Hatter's disease, because they thought that mercury had a magical healing power, and then also they thought that it would help them to live forever, and obviously none of them are still alive, so they weren't successful there. The third main general thing that people were doing if they were alchemists were they were trying to turn everyday items into gold, much like the demonstration that you just watched. So they were taking rocks and trying to make them into gold. They were trying to take copper and turn it into gold because money was power. The more money you had, the more power you had. And so they were trying to use science to their benefit in that way. Again, as you guys know, they weren't successful with that because you can't make an element. This is a video. You're going to want to watch this, so make sure that you go to your notes and watch that little video. Now, the first guy that we come to, we're in 400 BC. And in 400 BC, a guy named Democritus was a philosopher. And he sat around and he was thinking, because, you know, philosophers, they were thinking people. And these different philosophers were thinking about different things. And he said, wait a minute. If I have something, I can cut it in half. And then I can take that half and I can cut that in half. And I can take that half and I can cut it in half. And I can continually cut things in half and make it smaller and smaller and smaller until eventually I'm going to have a particle that cannot be cut anymore. Once you have a tiny indivisible particle, which he called an atomos, it just was something that you couldn't break down any further. So he said that the world is made up of these atomos, which are tiny indivisible particles that could not be cut down any further. He thought that they were spheres. Some of them were cube-shaped that he drew. But basically they were super, super, super teeny tiny things that looked like little spheres. This is a little golf ball that I'm going to use for a few of my show and tell type things. But the sphere that I have here, tiny indivisible particle, cannot be broken down anymore. So we're 400 BC. People didn't believe him. They didn't think that that was actually the case, and so they kind of discredited him. But it kind of sat there on the history books, and some people said, I think he's on to something. And then other people were like, no, he's crazy. So they kind of went back and forth about that. So that's going to sit in time. 400 BC to 1700, sorry. Well, we're going to jump ahead to this guy named John Dalton. At the end of the 1700s, he started to look at some of these works that Democritus did, and he said, wait a minute, I think he's on to something. And so he tried to explain some of these different concepts using new terminology that Democritus had said many, many, many years ago. So he called it Dalton's atomic theory. He put his own name on it because that's the joys of being a scientist. You get to put your name on whatever you discover or write. And with the atomic theory, he said that there are 5 things that actually help to explain the world around us. And we're going to look at the atoms themselves. Again, atomos, tiny indivisible particles. So he called it the atomic theory. Now, a theory is just a longer explanation of something that happens in the world around you. So, for example, a theory that you learned in biology is written by this guy. It's Charles Darwin. He had the theory of evolution. This little book right here is 703 pages long, and it is an explanation of his atomic theory, his theory of evolution. It can be refuted, which people argue about this all the time. But the theory is just taking what he's observing in the world and trying to explain it. A law on the kind of the opposite end of that spectrum is something that always happens. No matter what, a law cannot be refuted. If I drop a golf ball down, it's always going to go towards the center of the earth because of the law of gravity. Your bottom sits in a chair because it gets pulled to the center of the earth because of gravity. People say, what comes up must go down because of gravity. It's not really the physics terminology there, but it's a pretty short explanation. You had Newton's 3 laws. An object in motion stays in motion. Again, there's a little bit more to that I'll let the physics teacher take care of next year. But with that law, it's very short. It's condensed into one sentence. With gravity, if I drop this golf ball 100 times, 100 times it's always going to fall. It's not like on the 56th time it's going to stick to the ceiling, which would be kind of cool, but it doesn't happen. So laws cannot be refuted, theories can. Laws are very short descriptions. If you look at the word law, it only has 3 letters. Theories are longer explanations. The word theory has 6 letters. So theories are longer explanations, laws, I think I said that right, and then laws are short descriptions. Okay, back to Dalton. It's kind of a sidetrack on what is a law versus a theory. So we're back to Dalton, And he took these previous laws that people had, like the law of multiple proportions. You don't need to know that, but that was one of them that he took. And he tried to explain what is actually happening there. So it kind of looks like he stole other people's work and he put his own name on it. That isn't really the case. But he was just taking their work and trying to put new twists on it. So there are 5 parts to the atomic theory. You do not need to know the 5 parts. It won't say like, what is the 3rd part of Dalton's atomic theory? You need to know the general outline of his atomic theory. So the first thing, it's going to sound pretty familiar, all matter is made up of atoms. So all atoms are little these spheres like this. It's just like what Democritus said. If you have matter, it's made up of these tiny indivisible particles called atoms. If there's no atoms, it's not matter. If it's matter, it is atoms. So they're kind of interchangeable there. Second thing, if you have an atom of one element and an atom of the exact same element, they're going to be identical. So if this is oxygen and I have another oxygen, they're going to be identical to each other. If I have oxygen and I have nickel, they're going to be different from one another because they have a different mass, they have a different size, they have different properties and characteristics. So all atoms of the same element are identical. If you have different atoms of different elements, they're going to have different characteristics. So it should be common sense. The third part, he said that an atom cannot be created or destroyed. So just like the law of conservation of matter. Matter cannot be created or destroyed. It merely changes from one form to another. Same thing with the dividing part of it. He thought that an atom looked like this. And with that atom looking like this, there is nothing inside of there because we didn't know about the guts yet. So he would just say that an atom is just like a little sphere with nothing inside of it, tiny indivisible particles. The 4th part of Dalton's atomic theory just says that atoms come together in certain ratios to make a compound. For example, if you have water, water is H2O, 2 hydrogens and 1 oxygen. If you have a different ratio, H2O2, 2 hydrogens and 2 oxygens, that ratio is different, so you make a completely different compound. Water you can drink. Hydrogen peroxide, if you drink too much of it, it's going to make you vomit. 2 totally different things. And then the 5th part of Dalton's atomic theory, it just says that in order to make new compounds, you're going to go through a chemical reaction. When you go through a chemical reaction, you're going to take the different atoms of different elements that are chemically combined together. You're going to break them apart. They're going to reconfigure, and then they're going to go together in a different way. I kind of compare this to like preschoolers playing with Legos. Let's say one preschooler sits down with Legos. He makes a little house, and he's like, look at this little house. And then his friend says, I don't want to make a house. I want to make a car. And so they take the Legos apart with the house. They put it together in a different configuration, and they make a car. So we had one thing break apart, go together, make something new. That's all that happens in chemical reactions. The atoms break apart from one another. They go together with different partners. Now, Dalton was not 100% correct on everything. Dalton was wrong on a few different topics. One of them, he said that there were no guts inside of this atom. They were just tiny, indivisible little particles. We know now that that is not the case because the first guy that comes along, his name is J.J. Thomson. He's going to discover something inside of this little sphere that we didn't know about before. So we're going to refute that here in a second. And then also, we didn't know that isotopes existed at the time. An isotope is an atom of the same element that has a different mass because they have different numbers of neutrons. So with the atoms being identical, they're actually not. But again, we didn't know that when he got published, so he still gets credit for his atomic theory. All right, one more topic that we're going to talk about in these notes, and then this video is done, and then we're going to go to the history, and you're going to watch that tomorrow. With an atom, we're finally at a point that we can define what is an atom. It's a tiny indivisible little particle, it's a tiny little particle. Sorry, we're talking too much about Dalton and Democritus. And we know now that there are guts inside of this little sphere. With the guts that are inside of this little sphere that I have, if I take some of the guts out, they don't have the characteristics of that element anymore. So we know that there's protons, neutrons, and electrons there, but it's just the guts inside of the atom. It's kind of like the guts that are in my body. I have to have everything there to function like I should. But let's say that I take out my kidney. I'm kind of being gross, I know, but sorry. So let's say I have my kidney in my hand. It's going to look like a kidney, and it's going to function like a kidney, and I'm not going to function the same thing, without it. If it was identical, like I would take out my kidney and it would be a little Dr. Gable running around with all my little characteristics. That's not the case. So yes, there are guts that are there, but you can't break it down anymore and have the characteristics of that element anymore. So if I take out protons, I'm making new elements, which is nuclear chemistry. So an atom is the smallest little bit that you can break something down and have the characteristics of that element that you're dealing with. Now, we have never, ever, ever taken a picture of one atom of one element. That's tough because I'm expecting you to know what is inside of an atom in this unit, but we haven't even photographed what it actually looks like. Everything that we've done so far is based off of math. So we get graphs and we put everything together, and we kind of get an idea of what something's going to look like. But this picture here that's kind of like red and kind of greenish and purple and pink, this is as close as we've gotten to photographing the actual atoms that are all lined up, but we still haven't even gotten close enough to see, like what's actually there. That's more the energy that's surrounding it than the actual atom itself. So as we look at these things, it does get difficult, and our opinion of as far as what an atom looks like has changed over time as technology has gotten better, as you're going to find out. So when we're looking at the size of an atom, just to kind of put it in perspective of how small it is, if I take an atom and I blow it up the size that I can hold in my hand and make it the size of an orange. So if I take an atom and blow it up the size of an orange, to keep the scale, I'm going to have to take an orange and blow it up the size of the Earth. So if I take an atom, make it the size of an orange, so I can hold it in my hand so I can study it. To keep the scale, I would have to take an orange and make it the size of the Earth. Some people like this, some people don't. If you don't like it, just forget that I said anything. Now, another way of looking at how small an atom is, this video clip, you're going to want to go back and look at this. I'm not going to play it in here, obviously, but watch this video. And then this website is really cool. It's called The Powers of 10. They had a book that came out. I have it in my classroom if you ever want to see it. But the Powers of 10 show you like zooming in by a magnitude of 10 and then zooming out by a magnitude of 10, just to show you how big and small things are. It's kind of cool to play with. So I dropped that link in there since some of you guys are sitting at home. And then another way of seeing how small an atom is. Here I've got a piece of paper. With my piece of paper, the thickness of the piece of paper, the side that would give me a paper cut if I keep like rubbing this back and forth. There are 1 million atoms stacked, one on top of another one on top of another one on top of another one, in order to make the thickness of the piece of paper. Not this length, not this length, this right here that makes it 3D. That's 1 million atoms. That's a lot of atoms to make up that little bitty teeny tiny little sliver. So atoms are super, super, super teeny tiny. We do now know that there are guts inside of here, so we're going to find out those in the next video. But for right now, as far as our journey goes, Democritus thought that an atom looks like this, and then Dalton thinks that an atom looks like this. Again, there's nothing inside of it yet. There's no guts or anything. So we'll pick up with the next video tomorrow.